All right, so today we're going to talk about the fundamental theorem of calculus, part 2. I'm going to start by defining g as this accumulation function. So g is the integral from a to x of f of t dt. And we know from FTC 1, the fundamental theorem of calculus, part 1, that if I take the derivative of g prime equals f of x. So FTC 1 establishes that derivatives and integrals are inverses.
Dad, would you stop that writing so we can go on our walk now?
So they're inverse operations, essentially. So this is going to inherently imply that g then is something called the antiderivative of f. So the process of taking an integral produces something called an antiderivative. And so usually what we'll use to denote antiderivative is the capital version of that function. All right, and all that means is that by definition, if I take the derivative of g prime, that means I'm taking the derivative of capital F. That's going to get me f of x, which is established in FTC 1. All right, so an integral, the process of taking an integral is really finding an antiderivative. So let's just do like a quick off-the-cuff example so that you can kind of see what I'm talking about. So if I want to find the integral of just x dx, what I'm trying to think about here is what is the antiderivative of x, meaning what function such that if I took its derivative would get me x? Well, I'm going to know it's going to have to be to the second power, right? Because then taking the derivative of that will get me back to a degree 1 polynomial. The problem here, right, is if I bring down the 2, that's 2x. That's not just x. So something I can do to try and account for that is give it a coefficient. So let's do, okay, instead of just x squared, what if I put in place a coefficient of 1/2 that I know will then cancel that 2 as it's being brought down. So now when I bring down the 2, I end up with 2 times 1/2 times x, which is then just x, which is what I wanted, right? So what we would say then is that the integral of x dx equals 1/2 x squared. We found the antiderivative. Again, antiderivative just means if I take the derivative of my answer, it gets me back to that integrand. All right, well, one other thing to think about is that actually this answer should be 1/2 x squared plus any constant. And the reason is, right, if I have 1/2 x plus some constant c, or sorry, 1/2 x squared plus some constant c, when I take the derivative of that, that's still just going to get me back to x, because the derivative of a constant is 0, right? So that still just gets me back to x. So really, we should make a little amendment here. The most general version of this is that g of x will equal some antiderivative of f plus a constant. Meaning an antiderivative actually gets you a family of functions that are vertically shifted, because adding a constant just creates a vertical shift. Right, so now how does this apply to the fundamental theorem of calculus part 2? Well, FTC 2 really just is going to show us how we deal with what we call definite integrals. So integrals where our endpoints, our limits of integration, are both constants. Okay, so let's do it. We're going to keep our definition of g of x as is. But we're also going to remind ourselves that, okay, well, this also equivalently means that g of x is an antiderivative of f, so g of x equals some capital F of x, some antiderivative of x plus c, right? And another way of writing that is that then f of x, I could just move the c equals g of x plus some constant. And I know you may be like, Toller, you needed to subtract that c over, but it doesn't matter because c can represent any constant, positive or negative. It just needs to represent a constant. All right, so we're going to start with that definition, and then we're going to look at what would g of a be defined as? Well, if I'm using the accumulation function definition, that's going to be the integral from a to, now I'm replacing my x with an a, so a to a of f of t dt. And we know from properties of integrals that when your upper and lower limits are the same, that's like trying to find the area under a single point, which is 0, right? Great. Well, this also equals capital F of A, right? Plus C. So now let's take a look at this. F of B, capital F of B minus capital F of A, using this definition, would be equal to G of B plus C minus G of A plus C. Whoop, I'm a little wild with my parentheses, plus C, which is just G of B. Now notice that my constants are going to cancel out, so minus G of A. Well, we just found that G of A is 0, so this is just G of B, which if we then go back to our accumulation function definition up at the very top, G of B would be the integral from A to B of f of t dt. All right, so what have we found here? The big connection is this. The integral from A to B of f of t dt is equal to this. F of B, capital F of B minus f of A. Meaning, to evaluate a definite integral, all we have to do is find the antiderivative of the integrand, so the function that we're taking the integral of, plug in the upper limit, plug in the lower limit, and then subtract them in that order. So that's your fundamental theorem of calculus part 2. It just tells us how we deal with definite integrals. And it's just important you understand what capital F is. It's an antiderivative of lowercase f, and they establish that right here, right? So that's our big takeaway. How do we deal with definite integrals? Find the antiderivative, plug in the upper limit, plug in the lower limit, then subtract. All right, let's try this. So the integral from 1 to negative 2 of x cubed. All right, well, thinking about the antiderivative of x cubed, we want to find the function such that if we take its derivative, it's going to give us x cubed. So in that case, we know it's going to need to be to the fourth power, right? Because then when I take the derivative, I would be back at the third power. But if I just use x to the fourth, when I take the derivative, I'm going to have a coefficient of 4 in front, which I don't want. So to counteract that, I'm going to put a coefficient of 1/4 out there. And we can always check our answers just by trying to quickly take the derivative and make sure we end up with the original function, right? And that would mean 4 times the fourth x cubed, which is x cubed, which is what I want, right? All right, so we have my antiderivative, which is 1/4 x to the fourth. And then you'll see a couple different notations. What you can do is give it one bracket and keep your limits of integration. So I would still have -2 here and 1 here. And this just indicates, okay, I've taken the antiderivative, I found the antiderivative, I haven't plugged in my limits of integration yet. And so now I'm going to plug in the upper one. So that's 1/4 times 1 to the fourth minus, plug in the lower one, 1/4 times -2 to the fourth. And the rest is just arithmetic, right? So I have 1/4 minus, oh geez, 2 to the fourth is 16, divided by 4 is 4, which is, oh boy, 1/4 minus 16 over 4, sorry, which is -15 over 4. Which is fine, because if we think of this derivative in terms of an area, all that means is that there's more area under the curve on that interval, or sorry, under the x-axis than there is on top of the x-axis. So, whoops, sorry, I didn't realize that was. So if I sketch this out real quick, you all know hopefully what a cubic roughly looks like. But at -2, x cubed would be at -8. So it'd be like way down here. At +1, x cubed would be at 1, so up here. And so this curve kind of looks like it's going like that. Oh no, wait. So we're finding the area between this curve and the x-axis, and the reason it's negative is because there's much more area here than there is here above the x-axis, right? And so remember, an integral is the net area between the curve and the x-axis, and in this case, the net area is just more negative than it is positive. All right, find the area under the parabola, y equals x squared from 0 to 1. So in this case, we're going to set up our own integral notation. So it's going to be the integral of x squared from 0 to 1 dx. And this one I'm going to sketch the graph first, just so that we can have some idea about where this is going. So at 0, x squared is 0. I'll call this 1. X squared would be 1. And so all of that is going to be above the x-axis. So we are going to expect to have positive area here, right? So we'll expect our answer to come out positive. All right, so what's the antiderivative of x squared? Well, you know you need it to be to the third power. And once I take the derivative of that, though, that would be 3x squared, so I'm going to need a coefficient of 1/3 to cancel out the 3. And again, you can differentiate this to make sure it's correct. Oops. And then I'm going to indicate here, all right, I've taken my antiderivative, I haven't plugged in my limits yet, and now I'm ready to plug in my limits. So 1/3 times 1 cubed minus 1/3 times 0 cubed. That's going to be 1/3 minus 0, so just a third. So you might remember this was one of the first Riemann sums that we did, and we noticed that as we used more and more rectangles, our answers got closer and closer to a third. And now we've actually done the calculus, and the answer is exactly a third. All right, let's do another. Find the area under the cosine curve from 0 to b, where b is between 0 and pi over 2. All right, so another one where we're setting up our own integrals. And our upper limit is just going to be pi over 2, the largest value of b. All right, so this is a trig one. You got to think about the antiderivative of cosine. Well, the derivative of sine is cosine, so the antiderivative of cosine is just sine. Again, because if I take the derivative here, the derivative of sine gives me cosine, which is what I want, right? And limits of integration, 0 to pi over 2. So I'm going to do sine of pi over 2 minus sine of 0. And if I think about my unit circle, sine of pi over 2, so that would be 0, 1. So sine of pi over 2 is 1. Sine of 0 would be right here. Sine of 0 is 0. So my answer is 1. Cool. So to summarize, differentiation and integration are inverse processes. The process of taking an integral is called anti-differentiation. And here are your fundamental theorems of calculus. So part 1 just establishes that an integral is the inverse of a derivative. And then part 2 shows us how to deal with definite integrals being where your upper and lower limit of integration are constants. All right, guys, good luck this week.